Yeah, thank you very much. Actually, I will take less than that. I think I will. Anyway, I would like to tell you about some effort to understand the basics of behind Unruh effect. This is based on a paper, last month's paper we wrote with Michele Arzano. And so let me start. Well, everybody knows that there are these puzzles of black hole mechanics or black hole thermodynamics. And it actually, everything started with Bekenstein, who in 1973 suggested that in view of the fact that the area of black hole is always rising, it's reasonable, and he actually provided some number of arguments in favor of assuming that the entropy of black hole is proportional to the area, to its area measured in Planck length, in Planck areas. And this kind of physical, but not really mathematical, not formal claim was confirmed 2 years later or 1 year later by Hawking, who actually proved that black hole radiate at the temperature, which is inverse proportional to its mass, which both actually fit into some framework that we now call the black hole thermodynamics. Well, but it was soon realized that there are several puzzles associated with the black hole thermodynamics and with this whole framework. Well, the first puzzle is if indeed the black holes have entropy, which is associated with the area of black hole, then one should really like to understand what are the degrees of freedom behind the black hole entropy. I mean, what entropies of freedom are that are counted by black hole entropy. And so this is something that we certainly do not understand. And the second problem is an information problem, because it seems that apparently if you take into account, if you really think about Hawking radiation and you extrapolate it to the case in which the black hole is not stationary anymore, I mean when there is some back reaction, but there are some claims that this back reaction really could not change much the overall picture. The basic problem is that the unitarity doesn't seem to be preserved in the process in which the black hole is formed, and it radiates back away and leaves nothing behind, or it leaves a remnant, which is by itself a problem. There are many ways, and many people tried some approaches to try to understand this, but I think that there is generally an agreement in the community that these two aspects of black hole thermodynamics are still not completely understood, at best. Well, crucial to this thermodynamic puzzles is the quantum temperature perceived by accelerated observers, but not by inertial one. I mean, one of the major property of black holes, and one of the features that lies behind this firewall story, is that the accelerated observer actually sees or finds himself in a thermal state, but the inertial one actually, as in agreement with equivalent principle, should actually see himself in the flat Minkowski space with no temperature, of course. And therefore, I think it would be pretty interesting to actually try to investigate this property of temperature associated with accelerated observer in terms of the minimal setup. I mean, strip it down to the bare minimum, and this is basically the goal. This investigation that I want to describe to you, these investigations are about. Well, a little bit of history. Then equivalence between the notion of particle for Rindler and Minkowski space was noticed already almost 50 years ago by Fulling, even before the work of Bekenstein and before the work of Hawking. Well, then Unruh in 1976, and this is actually our starting point, in 1976, motivated by the discovery of Hawking, Unruh showed that there is a temperature associated with the presence of Rindler horizon. You can put it in different ways. That the most popular one is that if you are an accelerated observer moving in Minkowski space, you'll find yourself. You find yourself in the temperature which is proportional to the acceleration in the natural unit. Well, and there are claims that the presence of this temperature is actually the kind of a universal property of the presence of causal horizons, and in the terminology of Jacobson and Parentini. So this is kind of a very universal property, very basic property of physics. Once you have acceleration, you have temperature, and it would be nice to investigate what's behind it. Right. So I would describe the simplest system exhibiting a connection between geometric notion of boundary and thermal states. Well, basic to the Rindler situation is the presence of the light-like boundary, right? It's behind the whole thermal properties of Rindler spacetime, and I will use only minimal setting, only group theoretical ingredients associated with the symmetries of spacetime. So, well, it's probably not completely honest to say that I will not use no quantum fields, no spacetime, and well, certainly no metrics, because these things will kind of lure in or at least I will use some analogies or some knowledge from the general properties of quantum fields and general properties of spacetime. But in principle, the proof that or the construction I would like to present is purely algebraic and a pure representation theory. So let me start with the Rindler space. There is one thing, I mean, everybody knows Rindler space, but there is one thing that I think is interesting. So if I consider an accelerated word line, you know what Rindler space is. Rindler space is essentially a wedge, right? A wedge, a right wedge of Minkowski space. So if I have an accelerated observer, the word line of accelerated observer is, as you can easily convince yourself, nothing but the Lorentz orbit, which means that I can parameterize a point on the orbit by the magnitude of boost or magnitude of Lorentz transformation. So Lorentz transformation moves points along the orbit, and if you want, you can actually make a coordinate on the Rindler space just by assuming, or by, there will be a picture there in a moment, but basically you may say that the Rindler space, the coordinates of the Rindler space, which are actually canonical coordinates of the Rindler space, are just, you know, the Rindler space can be actually split into orbits of Lorentz group. So what is the transformation that actually translates from one orbit to another? This is something that came as a surprise. It's pretty obvious, but it came as a surprise to me, and I believe that many people know it, but I didn't, and I think it's pretty interesting that actually the transformation that moves from one orbit to another is actually dilatation. And the orbit of dilatation is basically this one. That means that you can actually use the coordinate on Rindler space. This is the Rindler space, the left wedge, denoted by 1. So you can use the coordinates on the Rindler space in which eta is a Lorentz boost parameter and psi is a dilation parameter, which tells you that essentially the Rindler space is nothing but a group formed by the boost and dilation, right? These are the coordinates. Sorry, I'm not too good in this. So basically the coordinates on the Rindler space are those. This is the translation between Minkowski coordinates t and x and the Rindler coordinates eta and psi. And I would like to stress again that this parameter eta and psi can be identified with the parameter of the boost and the parameter of dilation. All right? Which tells you something pretty important. You know, if you look at the textbook derivation of Unruh effect, you will find that essentially what you do, you compare the modes associated with the translation operator, I mean the plane waves in Minkowski space, right? Which are nothing but the modes associated with the Minkowski space translations, P, T, and Px. Well, you know that in quantum, essentially the plane waves are the, there might be some, there is a fancy mathematical description, but basically they are the eigenfunctions of the translation operators with some particular property. So we have the translation generated by infinitesimal generators of translation in Minkowski space, Pt and Px, which are the plane waves in the whole Minkowski space. And similarly, we have two translation operators, which are boost and degenerating translation in Rindle space. Well, I put the parameter A, which is the dimensionful parameter of which is a scale, of acceleration, but more generally is an inverse length scale of the problem. I put it to 1 just to simplify the algebra, and I will reintroduce it at the very end. So basically, returning to this textbook derivation of the Unruh effect, what you really do, you compare or some kind find how many particles of associated with Minkowski generators there are in the particles generated or the modes generated by Rindler space. So if I have a Rindler vacuum, you'll find that the Rindler vacuum is containing a thermal distribution of Minkowski particles. So basically, it turns out, I mean, if you look at it from this perspective, it turns out that the whole setup basically it basically boils down to the properties of this algebra. This is the algebra of two commuting translations in Minkowski space, Pt and Px. There are two dilation. There is a dilation and the boost. Well, there are non-trivial commutators of n with P, and there's another non-trivial commutator of which for some reasons actually I couldn't find here, between D and P, and D acting on Pt gives you Pt, and D acting on Px gives you Px. Okay, so now we have two sets of translation operators, and we know from quantum field theory that the eigenfunction of translation symmetry generate symmetry generators with positive eigenvalue of time like 1. So I have usually in quantum field theory, I have the time direction and the space directions, possibly. And we know that what the particle is. Well, the particle is the eigenvalue, the eigenfunction of the symmetry of translation symmetry generators, which has a positive eigenvalue with respect to the time like 1. This is a positive energy state, which I call the particle state. So this eigenfunction of the satisfying this property has an interpretation of one particle states. Okay, so let us try to simplify this problem further. Or we can form the light cone generators just by combining Pt and Px and N and D in the following way. And they actually, it turns out that these light cone generators actually satisfy an even simpler algebra. These are actually two commuting copies of the plus algebra and minus algebra. And the only non-trivial commutator is P plus with, or P with R equals plus minus IP. And in fact, this is the group associated with this Lie algebra is called the AX plus B group, and it plays some important role in mathematics. And one of the reasons is probably that this algebra here, with one sign or another, is actually the simplest possible non-trivial Lie algebra that you can think of. It contains two generators, it has one non-trivial commutator, so it's certainly the simplest algebra you can think of. There is, so this generator is actually P and R define the affine transformation of the real line. Okay, so let me concentrate on actually on the half of the algebra, which is described like this. I have a generator P and generator R, which satisfy this kind of a commutation relation. As I told you, this is the simplest algebra. And now I would like to argue that the physical or geometrical description of the algebra is essentially that it has to do in a very simple way. In a very simple way, it actually describes a line which is split into two half lines. And I will show you how it comes about.
Why I? Why is it imaginary?
Oh, well, because, because I want these generators to be anti-Hermitian, right? So in fact, I will use the functional representation of this algebra, not the matrix one. But it, of course, is not important. Okay, and as you will see, what's really important that P is a translation of the line. So P acts on the whole of the line, while R is a translation on the half line. So this is actually basically this algebra describes the basic feature of the situation in which I have a system with a boundary. I mean, I started with a system with a null boundary, but this is so this is basically the one-dimensional system with a boundary where P operates as a translation of the whole line, while R actually operates as a translation on the half line. Okay. So when I have an algebra, I'm actually try to find what the representation of the algebra are. And then after I learn about these representations, I will show you that using just the representation tree, I'm getting to the Unruh result. I find some thermal distribution of one state in another when I decompose one state in respect to another. So first of all, remembering the story of quantum field theory, let me define the following representation of P. So I have a states which I called x plus minus k with the positive or negative eigenvalues, and actually the states k I will call the P particle state because they will correspond. And actually, if you think about this in terms of quantum field theory and you play a little bit, you find that these plane waves that you obtain in this way are indeed exactly the positive energy plane waves. So the positive energy plane waves in this two-dimensional Unruh problem have in one-to-one correspondence with the states which are eigenstates operator P with the positive eigenvalue. Well, there is an inner product, so I can construct the field Hilbert space. The inner product is defined only for positive k, or kind of a positive energy. And it has this form. There is a resolution of identity, and the states are normalized in the following way. We define the states like those, P particle states, right? And we keep it in mind that, again, as I told you, they have this analog, so they are this analog of one particle states of quantum field theory. Okay, but we can play before we play the same game in the Unruh coordinates or in terms of R operator. Let me actually go to the Fourier space. We can find we have a positive energy state, so I can form the character defining the positions. The positions satisfy the range of positions is from -infinity to +infinity. they satisfy this resolution of identity, they are normalized to 1. And with respect to this, with respect to the x variable, the p has a representation as a normal momentum, so that's normal quantum mechanical momentum, while r is kind of, well, it's something else, but this is kind of an, this is, if you know, this is nothing but the dilation operator. And again, k is defined to be one particle state. Okay, we can do the same story. We can repeat in the r sector. I can introduce some coordinates, so I can play exactly the same game, in which I would like to introduce some coordinates and the dual coordinates in such a way that r actually acts as a translation in psi, where psi goes from minus infinity to plus infinity. I define the dual momentum. This is the character. This is the so this is this state. Omega is actually one particle state with respect to r operator. So in the case of the Unruh problem, you will call this states the Rindler space particles. Okay, the story is the same, and you find that with respect to this psi and omega, r is a translation, and p is a kind of a funny operator which has this form. All right. So now I would like to find what is actually the relation between one and another. At least on the, on the positive half line, there should be the relation between one and another. And actually, it's pretty easy to find. Sorry. Let me see. Right, it's pretty easy to find. The r, which has a representation, which is a translation in psi, in psi position or Rindler position, actually is we know that this is a dilation operator in the x space, which tells you that there is a relation between the x and psi, which is of this form, which has the Polynomial solution, right? And the same thing here. I know that P is the translation in Minkowski space, so it can be expressed in this way in Rindler coordinates, which again gives me this equation. Well, the space coordinates psi of R representation, which is important, they cover either the positive or negative half of the spectrum of the space coordinate x. Well, because e to psi is actually positive always, so x, so if I choose the sign to be plus, then there is a one-to-one correspondence between psi and the x. So there is a correspondence between psi and positive x, or there is a correspondence with psi and negative x. This is something that you may choose. So let me focus on this possibility, which is just the standard one, in which psi is the space, is the coordinate. In this Unruh problem, in the Rindler space, this is the Rindler coordinate. This is Rindler space coordinate. This is the Minkowski space coordinate. The relation between these two is this. And there is an isomorphism between the state, which is the eigenstate of psi, and the positive x, which is defined in this way. There is eigenstate between the coordinate in Rindler space and the positive part of coordinates and of Minkowski coordinates. Now we can actually, well, we know, since we know what is the, I think this again disappeared. So this is psi with omega is given by the plane waves, and it follows that x with omega has this form, and vice versa. We know that the Minkowski space plane waves that can be translated into, so a plane wave in Minkowski space, or the positive energy solution, or the positive or the one particle state in Minkowski state can be expressed in terms of psi coordinate or Rindler coordinates in this way. Well, there is a subtle point, because I would like really to extend both the, well, the translation, the Minkowski translation moves acts on the real line, but R, so far, acts only on the half line. But it can be extended. The only sample point is that P, so let me show it to you, P actually always acts, P is a derivative, right? So P always acts to the right. Well, the R actually acts to the right. This is the dilation operator, so it acts to the right on the, on the right part, or on the right half line, and it acts to the left on the left half line. So in order to have the same orientation, instead of using x dx, so R on the R everywhere, I use the operator R, which is defined on the left half lines here, and the minus R, which is defined on the left hand line. This is a little bit, so there is a bit of technicalities, and we have some characters of these representations. So you may say that this is the definition of Fourier transform between different subspaces. And let me actually summarize so far what we have. We have this representation of, representations of the P and R. Well, for P, I have the momenta, because P is a kind of translation, so I have just momenta, which is split it into positive energy and negative energy solution. I have positions X, when we started are just, they might be either positive or negative. Then I have the same construction in the half line here. I have the energies, Rindler energies omega, which can be split into positive energy and negative energy. So these are actually these are the one particle Rindler states, and these are one particle Minkowski space. And there is an associated position psi, which in the case of Rindler actually is a Rindler coordinate, so it actually covers only half line. Okay, now we introduce another position for the Rindler space, which is psi bar, which covers the other half line, or you may say that this is the one that covers the region 3 of this standard Rindler space picture, or the right wedge. And associated with this, you have a positive positions in Minkowski space associated with a positive half line, and negative position Minkowski space associated with the minus line. All this can be actually obtained purely from the representation theory of the group of the algebra we started with. So now, let me get to the point. Well, I need some decomposition of unity, and you can prove that you can use the decomposition of unity for x's, so the position, you can decompose the states which are eigenstates of position operators on Minkowski space into positive, guys that belong to the positive line, and the guys that belong to the negative half line. And this is the decomposition of unity. So any position, you may say, well, the position state can be decomposed into, so that there is a basis of the states which has as a part the position that belongs to the positive half line and the position that belongs to the negative half line. There are this is the normalization of the state, and then what we can find, we can actually, because I have this decomposition of unity. Now what I can do, I can actually take omega state, so the state which has a given Rindler energy omega, and decompose it actually into this basis. And this decomposition takes this form. There is this funny x to minus I omega and x to I omega coefficients. Well, it's kind of essential here that we actually take care of normalization, because at the end of the day, I would like to ask myself how many Minkowski particles are there in the state that is defined by omega. So I need to make sure that I have a correct normalization, so that this state is indeed the one particle state, in the sense that it contains one particle per unit volume. And this is the correct normalization. Okay, right. So now what I can do, I can actually calculate the overlap between the two. So I can actually calculate the overlap between the one particle state in Minkowski state and one particle state in Rindler state. And the overlap, actually you can calculate it. It turns out to be nothing but the Mellin transform, which is defined in this way, and it's expressed in this way. So now I can actually ask myself how many p particles there are in the state omega. So I have a state omega, which is a state, one particle state of the in Rindler space, and then I ask how many Minkowski particles there are in this state, and what we find is actually nothing but the Rindler thermal distribution. So actually we see that there is a thermal spectrum of the so the state which is one particle state with respect to Rindler observer is actually nothing but the so well put it different way. The one particle state, the Rindler space contains actually the whole is actually a thermal state here. So what we find is that the state omega, which is the Rindler state, actually carries a thermal distribution of p particles, which are Minkowski particle, at the temperature which is 1 over 2 pi. And if I reinstate the acceleration parameter, this gives exactly the Unruh temperature. So if I, as you remember at the beginning, I actually put a equal to 0, which was the scale of the problem, so I didn't want to make this algebra more complicated than necessary. But when I restate it, so trace how it actually how this parameter appears in different stages of derivation, I find that the temperature is actually I found the expression which is exactly the Unruh expression for the temperature for the particle in the Rindler space or Rindler space observer. Okay, so what time is it? Okay, so I'm closing. Let me just make a summary. Well, so let me say, I mean, the steps of the derivation are kind of technical, but I would like to stress that all the steps are essentially the representational theory of a particular Lie algebra. So I started with a Lie algebra. I argued that this Lie algebra is associated with the symmetries of two-dimensional Minkowski space with a boundary. It describes actually the situation in which I have a Minkowski space, like boundary, which splits this Minkowski space into two parts, and there are two translations, one which operates in the whole space, and another which operates only in the half line. So I described the system exhibiting the connection between geometric notion of boundary and thermal quantum states, and then using purely the representation theory, I found the result that that there is a relation between this algebraic structure and the thermal quantum states, which I think by itself is kind of interesting, and in a sense, kind of straightforward, more straightforward than the standard derivation, which are based on quantum field theory. Well, but you should remember that the Unruh effect is kind of universal. I mean, if you think about the black hole, then you can think about Hawking radiation, or at least approximate the Hawking radiation, just by thinking about the near the horizon geometry and find that this thermal state, which corresponds to Hawking radiation, is actually exactly the Unruh state as seen by the observer, which is the near the horizon observer. So it seems to indicate that since this algebra is the algebra of symmetries that I started with is kind of natural. This is a natural setup or natural framework for describing the system with a boundary. It actually captures this algebra actually captures the essence of not only of Unruh effect, but possibly also of, so it plays some role might play some role in understanding of Hawking radiations. Okay, and then what next? Well, this is the property of A. You can think about it also in different way. I mean, this is the property of representation of AX plus B group, which plays a kind of important, kind of interesting role in several approaches. I mean, it's interesting for members of completely disconnected communities like non-commutative geometry, because the formation theory of this algebra is kind of interesting, affine quantization, quantum cosmology, etc. So perhaps this thermal property of this algebra might be of interest in this context. And of course, it would be nice to see if this thermal properties might be of any use in the context of these applications. And also, and last but not least, I think that, you know, if you think about, because the system I was considering was effectively one-dimensional, so I started with a two-dimensional system, but effectively the relevant part was one-dimensional. But I think that even if you think about the high-dimensional situation in which you have kind of a flat null surface and a normal, and if you assume, so if you are in a very small region in which even if you have non-trivial gravitational field, if you can assume that the situation is almost flat, then basically you have single direction, which is direction perpendicular to the boundary. There are some direction along the boundary, but in this direction perpendicular to the boundary, you can actually have exactly the same situation as we had before. So exactly in this direction, there is this AX plus B group or algebra operates. So it seems that the thermal property, this thermal property discovered here, might actually be also used in, or might be of interest in the investigations of the generic systems with boundaries in both, in quantum gravity. And I think this is what I wanted to say. Thank you.
This is very nice. So I have a comment and a question. I know a similar derivation that is algebraic, fully algebraic in the same spirit, but uses the full Poincaré group. That's Bisogniano-Wickman theorem. Generally formulated by introducing things that sound really like a quantum field theory, but the ingredient is really you're using properties of the Poincaré group. And the derivation is much simpler because we are just using this AX plus B group.
Well, I probably forgot to stress, but sorry for interrupting you, that the essential part of this is that you have not Poincaré but Weyl-Poincaré group. So the essential part is played by the dilation operator.
Yeah, so that's exactly the question I wanted to ask you. So is it correct to interpret this derivation not as a line that I could think of it as a line in space and then I take half of the line, but as I take a null generator on my irregular horizon, null array, and I just look at symmetries of that. That is null translations and null dilatations. And
null boosts.
Yeah, would be boosts.
Well, okay,
which
boosts.
is translations and dilatations.
Right.
Yeah. Which is exactly the group, I would say, AU plus B, where U is the affine parameter.
Yes.
You're calling X.
Yes.
So in this sense, this is the same algebraic logic, and it would apply to the two uncoupled sectors of 1 plus 1 field theory. Left moving and right moving.
Exactly. Yes, that's what that's why I'm actually making this picture, because I think that the use of this it goes beyond just the simple setup that I'm presenting here. And of course, the first thing to do, and actually this is something that we're doing right now, is to try to calculate, because this setup also seems to be pretty convenient to compute the entanglement entropy, right? Because you have this the decomposition of states, so you can compute the entanglement entropy almost immediately. So and this is interesting to do it in one dimension, you do it in higher dimensions. I don't know the result yet. I didn't finish the calculation, so I don't want to talk about it. But I think that in many, I mean, this is just the beginning. I think it's quite interesting, not because of this particular construction, but but I have a feeling that this construction is actually generic for many interesting situations. Yes.
A brief question about you said that one can easily reinstate the acceleration which was set equal to 1. I just wanted to ask you, do you have in mind something that doesn't go through quantum field theory?
No, I mean, this is
putting a detector and a quantum field that you can do completely
well, you know, the physical interpretation in the Rindler space. I mean, the putting the Rindler detector that it clicks when, you know, it's a completely different story, right? I mean, one thing is the thermal state, and the second thing is it possible in principle or in practice to measure the properties of the state? Well, actually, the A is pretty simple. If I have this algebra PR, which is P, then if I want naturally to represent this has a natural dimension of inverse length or momentum, right? So there is no problem. But if but this guy is, if you start with n plus d, it's dimensionless. So in order to make it dimensionful as you want, if this thing is gonna be translation operators, then I need to have a scale which is, so I need to make it given the dimension of inverse length, which means that I need to put the parameter of the dimension of inverse length. This is just a pure dimensional analysis. So this parameter, particularly this parameter, does not need to be the acceleration. It might be any other parameter of dimension of inverse length, depending on the context.
Other questions? Okay, thank you again.
Thank you.